Assalamu alaikum. This is our third lecture discussing chapter 4. This lecture is supposed to be on Wednesday, 25th of March. Today we'll start discussing how to compute expectation and variance in case of the continuous random variable. Before going through the formula, let's start first. Remember this formula in the case of the discrete random variable. In the case of the discrete random variable, when we have y is discrete random variable y, and y is having the probability mass function, which is b of y. Then if we need to find the expectation, which measure the center of the probability mass function, this can be expressed as or computed as the summation of all multiplication of all values of y times its probabilities. This summation is computed all over the values of y. On what we do now in the case of the continuous random variable, in the case of the continuous random variable, all what we are doing now is to replace the probability mass function with the probability density function. So instead of using probability mass function p of y, we are using f of y. And instead of using the summation, we'll use the integral. So now we can conduct, or we can expect the computational rule or the formula of computing the expectation in the case of the continuous random variable to be, if we have y is a continuous random variable that is defined by the probability density function, that is f of y, then the expected value of y is computed at the integral all over the values of y from negative infinity to infinity for the multiplication between y and the probability density function. So this is the rule in the case of the continuous random variable. Now let's try to read the definition. For a continuous random variable y, have the PDF defined by f of y. The mathematical, we call it mathematical expectation of the random y, the random variable y denoted by expected value e of y, is given by, this is the formula that we just discussed, assuming this integral is exist, and the existence of the integral mathematically is defined by this condition. If this condition is satisfying, then this integral is exist. Expectation of a function of a random variable. Now we are generalize the definition of the expectation. If you are taking a function and this function have to be one-to-one function, g of x, you are defining a continuous random variable y having BGF and that is defined by the BGF f of y, then for any real valued function g, the expected value of this function equal to the integral all over the values of y from negative infinity to infinity for the multiplication of g of y times the BGF, provided that this integral is also exist. If we try to try to detect the interpretation of the expectation. If remember the case of discrete random variable, to give an interpretation to the meaning of expectation, we'll start with the discrete random variable. Just to remind you, if we imagine that we have a random variable y that is a discrete random variable, and the variable is defined by the probability mass function b of y, and this is the probability histogram. So the value y here just took 7 values from y1 to y7, and each of them is represented by a bar. The height of the bar represents the probability that the random variable take this value. The formula for the expectation of the random variable y, in fact, is the weighted average of the random variable y, and the weights are their probabilities. So the variable that are represented in the probability mass function with a higher probability are most represented to the distribution. So we expect that the expectation will be close to these values. So the values with the higher probability are very close to be the expectation of the random variable. So if we look at this histogram or the probability histogram, we'll find that the values y5, y6, and y7 are most represented by a higher probability from the height of the probabilities here, and the value y6 is more represented by the highest probability. So we can expect, if we compute the expectation in this case, that the expected value of y will will be very close to the value y6. In fact, we in the continuous case we also are making something like the weighted average, but here y doesn't take a certain value. Y take value over the values, over the range over which PDF is defined. So here y take any value between or within the range of A and B. So we'll take also the multiplication of the values of y over this range, and these values are weighted by the PDF. But instead of summing this weighted average, we are making the integration. We are computing the integration all over y is defined, or all over BDF is defined, which is defined over the interval from A to B. So in this case, we have the BDF is increasing when it's close to B, and when it's close to A, it's increasing. So we expect that the expected value will be around, our value is close to the value A, because here in this area we have the higher probability, which is represented by a higher or the highest values of the BDF. This was the interpretation or the meaning of the expectation. Now move to another measurement, which is the variance. And if you remember, again, we studied variance, and the variance was a measure to center the spread of the values from its mean. A special case of a function of a continuous random variable y is g of y, such that g of y is the squares of the distance between y and its mean. If we express mu at the expected value of y, so y minus mu all to the power 2 are the squares of the values of y from its mu, or the distance, or the square of the distance of y from mu. Then the expected value of this function, in fact, expresses the expected value of its squared deviation from mu. Hence, this expected value indicates to the variance. And we can measure this by this formula. In fact, this is the same formula that we have studied in the discrete random variable. And if we remember, we have two formulas, the theoretical formula and the computational formula. In fact, in the computation, we directly use this formula. So the variance equal to the expected value of the square value of y minus the square of the expected value. The variance show how for a set of values of the random variable y are spread out from their average value. By the way, the average is similar terminology to the mean or the mathematical mean. Another important measure of spread is the standard deviation. We know that the standard deviation is just the square root of the variance. Now move to studying some properties for the expectation and the variance, and in fact they are the same properties that we discussed in the discrete case. So if we have A, B, C1 up to Ck are all real valid constant, and the function G and G1, G2 up to Gk are functions of the random variable of y. So the expected value of a constant is the same constant. And we have if we define another variable, say for example z, and z equal ay plus b. So the expected value of z, if we express this as z, then the expected value of z will be the a اللي هو constant times the expected value plus b. If we generalize this property to another property. And instead of using the random variable y, we are using a function of the random variable y. Here we have two functions. The expected value of the sum of these two functions, and each of them are multiplied by a constant. This will be the expectation, the first constant times the expectation of the first function plus the expectation of the second function times the constant. If we generalize more, instead of have just two functions, we have k function. So we're applying the same formula. Now moving to the properties of the variance, we know that the variance of a constant equal to 0, and then if we have a variable equal to a constant times the original variable y, then the variance of this variable will be a square times the variance of y. If we have a variable, another variable equal a constant a times the variable y plus or minus b, this will be a to the power 2 variance y. All these formulas are discussed in the discrete case, and in fact we prove them. Now move to discuss some exercise over the expectation and the variance. Here we'll start with example number 1, and I just want to inform you that all examples in the lecture slide are answered, but I will answer them with you. Let y be a continuous random variable with probability density function given by this form. First, we need to find the c. C is the constant that make this BDF is a valid BDF. So if you remember, we discussed answering a question like this in the last lecture. So we'll move to applying the condition of the BDF to find the value of C. We know that the integral for the BDF all over the range from negative infinity to infinity have to be 1. This is the concept of the probability density function. Then we have this BDF is 0 other than the range from 0 to 1. So this integral will be from 0 to 1. Then we'll substitute with the value of the BDF c y squared 1 minus y dy equal to 1. So we have here c, can we bring c outside the integration from 0 to 1, and then multiply y squared by the bracket. So we'll have y to the power 2 negative, y to the power 2 negative, y to the power 3 dy, all this equal to 1. So if we'll apply the rule of the integration, this will be y to the power 3 divided 3 minus y to the power 4 divided 4. Substitute with the limits of the variance from 0 to 1. Then substitute for this limit, give us 1/3 minus 1/4 equal 1. So this will be c divided 12 equal 1, then c equal 12. So the BDF will be in the form 12y to the power 2 1 minus y, and y is defined within the interval of 0 and 1. Then move to the exercise to discuss the next question. We need to find the expectation and the variance. To find the expectation, all what we need is to apply the formula of the expectation. We know the formula of the expectation. The expected value of y equal to the integral from negative infinity to infinity to the multiplication of y times the BDF. Then we'll have here y times 12 y to the power 2 1 minus y dy. So we are multiplying the BDF times y, and then integrate this all over the value over which the BDF is defined, which is here from 0 to 1. Here we'll have 12 here as a common factor, then y times y to the power 2 times 1 equal y to the power 3. Negative y times y to the power 2, which is y to the power 3, times y, which is y to the power 4. And then we'll substitute from 0 to 1. This will give us I'm sorry, we did not find the integral yet. I'm sorry, we're just all these, just the multiplication. But here we still have 12 outside the bracket, and then we are integrating from 0 to 1 dy. Let's move to the left side to continue solving the question. This will be 12 y to the power 3, integration of y to the power 3 will be y to the power 4 divided 4, negative y to the power 4 will be y to the power 5 divided 5. And then we'll substitute from 0 to 1. This will give us here 1/4 minus 1/5, and then when we substitute with 0 for both terms, it gives us 0. So here we'll have 12 divided 20. 12 divided 20, if we simplify this fraction, divide both denominator and numerator by 4, this will give us 3/5. This will be the expectation. And now to find the variance, we know that the variance is computed as, computationally, at the expected value of y square, okay, negative expected value of y all squared. So we need first to find the expected value of y square. Now move to the next page. Expected value of y square. We will consider y square as a function of the random variable as if it is g of y. So the expected value of g of y is the integration from negative infinity to infinity for the multiplication of this function, which is g of y here represented by y to the power 2 times the BDF. Y to the power 2 times the BDF. Again, this will give us integral from 0 to 1. Here we have 12 as a common factor. Then y to the power 2 times y to the power 2, which is y to the power 4, minus y to the power 5 dy. This will be 12 times y to the power 5 divided 5, negative y to the power 6 divided 6, and then we'll substitute with the integral limits. This will give us 12. Here we'll have a common denominator is 30, and then 6 minus 5, which is 1. So expected value of y to the power 2 equal to 12 divided by 30. If we eliminate both by dividing both values by 6, this will give us 2 divided 5. This was the expected value of y square. Then the variance of y will be this expectation negative the square of the value of the expected value. Here we have the expected value. Here we find it as 3/5. Fine. Then this will be 3/5 all to the power 2. So we have 2 divided 5, negative 9 to the power 25. This will give us 25. And then 25 divided by 5 equal 5 times 2 equal 10. 10 minus 9, this will be 1 divided 25. This is the variance. So we have expectation is 3/5 and the variance is 1 divided 25. Here we have the expectation is 3/5 and the variance is 1 divided 25, and also the expected value of y squared equal to 2 divided 5. Now we have a random variable, say x, and x equal to 2y plus 3. And we need to find the expectation and the variance for this random variable. Let's try doing this. We are here defining a new random variable from y, which is x equal to 2y plus 3. Let's check. We are writing the correct formula. 2y plus 3. Yes, correct. 2y plus 3. And we need to find the expected value of x and the variance of x. of the expectation and the variance, we'll find the expected value of x and the variance of x. We have here expected value of x. We'll substitute with the expected value of x with its relation to y. So this will give us expected value of 2y plus 3. Here we have ay plus b. A equal 2 and b equal 3. This will give us 2 expected value of a. 2 expected value of y plus expected value of 3, which is constant, equal to 3. So we'll substitute just in this equation by expected value of y, which is 3 over 5. So we have 2 times the 3 over 5 plus 3. This will be 3 times 2 equals 6 divided 5 plus 3. So this will be 21 divided 5. This will be the expected value of x. Then move to find the variance of x. This will be the variance of 2y plus 3. We know that the variance of 3 equals 0. So we need to find the variance of 2y. Variance of ay is a to the power 2 variance y. So this will be 2 to the power 2 variance of y. So this will be 4 times the variance of y is 1 divided 25. So the variance of the x will be 4 divided 25. Move to the answer to check our answers, which is find the expected value of x equal to 21 divided 5 and the variance of x equal to 4 divided 25. Now move to another exercise to give more practice. Here we have a variable representing the proportion of time that an industrial robot is in operation during a 40-hour week is a random variable with probability density function given by 2y and y between 0 and 1. Find the mean and variance of the proportion of time that the robot is in operation. We need to find the mean and the variance of y. Here we have proportion, so proportion of time. Because proportion is a fraction always between 0 and 1, so y represented the proportion, so y here takes the value between 0 and 1. We have a function here which is 2y, and we need to find the expected value and the variance of the proportion of time the robot is in operation. Here we have the function is 2y. We have f of y. We have f of y equal to y, and y takes the value from 0 to 1. I need to find the expected value of x, of y asfa. Expected value of y based on the definition is the integral from negative infinity to infinity y times the BDF of y dy. Then this will be, if we substitute for the BDF as given by the formula here, we'll substitute for the limits over which the BDF is defined to be from 0 to 1, and then we have y times the BDF, which is 2y dy. Then we are giving the integration of 2y to the power 2 dy, and we have this integration is computed from 0 to 1. This will be 2 times the integration of y to the power 2 above function. This will be y to the power 3 divided 3, and then substitute from 0 to 1. This will be 1/3 minus 0. So the expected value is 2/3. This is the expectation, 2/3 proportion. To find the variance of y, we need first to find the expected value of y to the power 2. Expected value of y to the power 2 will be by definition from negative infinity to infinity y times f of y dy. Then we have expected value of y to the power 2 equal to the integration from 0 to 1 y to the power 2 times 2y. This is the value of the BDF. This will be 2y to the power 3 integral from 0 to 1 dy. This will be 2 divided 4 y to the power 4, and then we'll substitute from 0 to 1. This will be 2/4 minus 1 minus 0. So this is the expected value of y to the power 2. Then we'll substitute in the formula of the variance to be the expected value of y to the power 2 negative the square value of the expected value of y. I'm sorry, not the square value, I mean the squared value. So we'll have here 2 to the power 4 negative, I think we have 2 divided 3, which is 4 divided 9. Then we'll just to check the value. Yes, 2 divided 3, which is 4 divided 9. Then this will be 39 divided 4, which is 9 times 2, which is 18. 18 minus 16. This will be 2 divided 3, 36, which is 1 divided 18. 1 divided 18 is the variance of y. Now move to the question to check our answer. Yes, we have 1 to the power 2, the expected value. 1 to the power expected value is 2 to the power 3, and then expected value of the variance is 1 divided 18. Now, for the robot under the study, we define a new variable is the profit. The profit is defined by x. For a week is given by x equal to 100y minus 60. Find the expected value of y and the variance of x, 200y minus 60. We have x is the profit, 200y minus 60. And we need to find the expected value of x. Applying the rule or the properties of the expectation, this will be 200, the expected value of y, minus 60. The expected value of y was 2 to the power 3. So 200 times 2 to the power 3 minus 60. And then we'll find the value. For the variance of x, this will be the variance. This will be the variance of 200y minus 60, which is 200 to the power 2 variance of y, which 40 thousandths divided 18. Now move to find the final answer. Yes, here we have 40,000 divided 18, which is 20,000 divided 9, and here we have 220 divided 3. This is the expected value of x. Here we have another exercise, and I give you the final answer, so I need you to have more practice using this formula of the expected value and the variance, and try to detect that you have the same model answer. Now move to the moments. The moment is a general idea of the expectation. And if we remember, we study the moment in the discrete case. We have the same slides here, by the way. All difference that we have here is to use the integral instead of the summation, and we'll use the BDF instead of the BDF on the probability mass function. We define the moment, or we partition the moment into two types. We have a central moment and non-central moment. Non-central moment for a continuous random variable y with BDF f of y, the earth moment around the origin is defined by mu dash r, which is expected value of y to the power r, and any expected value of a function of a random variable all the time will be the integral of the multiplication of this function times the BDF, and we'll integrate all over the values of the y over which the BDF is defined. So this definition or formula does not differ from what we have in the expected value or the expected value of y to the power 2. Here we have r is more general than 2 or 1. So for r equal 1, here, this will give us the expectation, and for r equal 2, this will give us the expected value of y squared that we use to find the formula. So we have variance y equal expected value of y squared minus mu to the power 2. So the expected value of y squared equal the variance plus mu squared. And if r equal to 0, so e to the power y to the power 0 is expected value of 1, and the expected value of 1 equal 1. We call this the r non-central moment of y. It's we discussed the points 1, 2, and 3. Now move to the second part of the moment, which is the central moment, and here we are finding the rth moment around the mean mu, not the origin in the last case. So for the continuous random variable y defined with the BDF f of y, the rth moment around its mean is measured by mu under square r. This will be expected value of the distance of y from mu all to the power r. So again y minus mu, again y minus mu to the power r will consider as a function of a random variable. To find the expected value of this function, all what we need is to find the integral of the multiplication of this function times the BDF. And then we make the integration all over the values of the random variable. So we call this the rth central moment. If we here we have some different values for r that we already know. So if we substitute for r equal to 0, this will give us expected value of y minus mu all to the power 0, which is expected value of 1. So this will be 1. If we have r equal 1, we'll have expected value of y minus mu, which is the expected value of y minus expected value of mu, and here we have expected value of mu equal mu because this is a constant, so this will be mu minus mu, which is 0. And the end, if we substitute for r equal 2, this will give us the formula of the variance. Expected value of y minus mu all to the power 2, this is the variance that we already know. Now move to answering a question to cover the moments during an during an 8-hour shift, the proportion of time y that is a sheet metal stamping machine is down for maintenance or repair has BDF given by this formula. The cost in hundreds of dollars of this downtime due to the lost production and cost of maintenance and repair is given by C equal 10 plus 20 y plus 4 y to the power 2. So we have here y is a function of a random variable y, C is a function of a random variable y, and functional form, take this formula. Find the mean and the variance of C. To find the mean of the variable C, I think it's not a big deal. We just enter the expectation to this formula. But first we need to find the variance and the expected value of y, because we'll use these formulas here, so we need to find the expectation and the variance. Here to find the expected value of C, this means to find the expected value of 10 plus 20y plus 4y to the power 2. So we need to find 10 plus 20 expected value of y plus 4 expected value of y to the power 2. So we need now to find the expected value of y and the expected value of y square. Expected value of y from the formula of the BDF equal to the integration from 0 to 1 y times the BDF, which is 2, 1 minus y. This will be 2y minus 2y to the power 2, integral from 0 to 1 dy, which is 2 divided 2y square minus 2 divided 3y to the power 3, and then substitute from 0 to 1. This will be 1 minus 2/3, which is 1/3. So So the expected value of y equal to 1/3. Now move to find the expected value of y to the power 2, which is integration from 0 to 1, y to the power 2 times 2 times 1 minus y dy. This will be 2 divided third, 2/3 times y to the power 3 minus 2 divided 4 y to the power 4, and then substitute from 0 to 1. This gives us 2 to the power 3 now minus 2 to the power 4. This will be 12 here. 12 4 times 2 equal 8. 8 minus 6 equal to 2 divided 12, which is 1/6. This is expected value of y to the power 2. So we can see that the expected value of C will be 10 plus 20 times expected value of y, which is 1/3, plus 4 times expected value of y to the power 2, which is 1/6. So at the end we'll have 10. Can we use 6 here? So we'll have here 60 plus 40 plus 1 plus 4. At the end, this will be 104 divided 6. This will be the expected value of x. We can simplify the expected value of x by 552 divided 3. So if we simplify this fraction, this will be 52 divided 3. And now move to find the variance of C. We know that the variance of C, if we consider C as a random variable, we can apply the formula for the variance in terms of C. So this will be expected value of C to the power 2 negative the expected value of C all to the power 2. We already find the expected value of C, which is 52 divided 3. So we still need to find the expected value of C to the power 2. Expected value of C to the power 2 equal to the expected value of, substitute here for the value of C in terms of y. This is 10 plus 20y plus 4y to the power 2. Let's check the 10 plus 20y plus 4y to the power 2. And now we need to find this factor, which means the expected value of two brackets, 10 plus 20y plus 4y to the power 2 times the factor itself, 10 plus 20y plus 4y to the power 2. This will be expected value. This will be the expected value. Expected value of 100. This will be the expected value 10 times 10, which is 100, plus 10 times 20y, which will be 2000y, plus 10 times 4, which is 40, y to the power 2. I'm sorry about the pen. And so again, this will be the expected value of 10 by 10, which is 100, plus 10 times 20, which is 200, y, plus 10 times 4, y square, which is 40, y to the power 2, plus here we will multiply each term of those by this bracket. So we finish 10, we'll move to 20y. So this will give us 200y plus plus 400 y to the power 2 plus 80 y to the power 3. For the last term, this will give us 40 y to the power 2. Will continue in the next line. Then 20 times 4, which is 80 y to the power 3 plus 16, 4 times 4 to y to the power 2, which is 16 y to the power 4. And then try to add each similar y together. So we have a constant term, only 100. So at the end, this will expected value of 100 plus all terms with multiplied by y. We can fix them like this by another color. This is y, and here this y, and again we don't have any other y, so this will be 400 y plus y to the power 2. We have here y to the power 240, and we have 40 again, and we have 400, so we have 480 y to the power 2, 480 y to the power 4. I'm sorry, y to the power 2. 480 y to the power 2 plus 480 y to the power 2. And move to y to the power 3. We have 80 y to the power 2, y to the power 3, and 8, so we have 88 y to the power 3. At the end, y to the power 4. We have here 16, and we have here, we don't have any other y to the power 2, which is 16 y to the power 4. And then we'll enter the expectation. Here we have 100 plus 400 expected value of y plus 480 expected value of y to the power 2 plus 88 expected value y to the power 3, and at the end plus 16 expected value y to the power 4. So we need to find expected value y to the power 4 and the expected value of y to the power 3 at the first. Fine. Now try to remember the formula of the BDF. I think it was 1, 2 times 1 minus y, 2 times 1 minus y, and y between 0 and 1. So we need now to find expected value of y to the power 3. So this is the mu prime 3. Here we have the third non-central moment. Third non-central moment. This will be expected value y to the power 3, which is integration from negative infinity to infinity y to the power 3 times LBDF. Substitute for the limits for the BDF, which is a support of the CDF, which is from 0 to 1, y to the power 3 times 2 times 1 minus y dy. This will give us 2 y to the power 3 minus 2 y to the power 4. And this, we are integrating this formula from 0 to 1 dy. This will be 2 times 4 divided 4 y to the power 4 minus 2 divided 5 y to the power 5. If we substitute for the limits from 0 to 1, this will give us 2 fourths minus 2 fifths. If we try to use a common denominator 20, we have here 20 divided 4 equal to 5 times 2 equal to 10 minus here 20 divided 5 equal 4 times 2 equal 8. So this will be 2 divided 20, which is 1 divided 10. This is expected value of y to the power 3. Then we'll move to find the expected value of y to the power 4, which is mu 4 prime. This is the fourth non-central moment. This will be directly from 0 to 1. This will be from 0 to 1 y to the power 4 times 2 1 minus y dy. This will be 2 integral from 0 to 1 2y to the power 4 minus 2y to the power 5 dy. Then this will be 2 divided 5y to the power 5 minus 2 divided 6y to the power 6 from 0 to 1. this would be 2 divided 5 minus 2 divided 6. If we use 30 as a common denominator, this will be 12 minus 10, which is 2 divided 30, which is 1 divided 15. So we have here expected value of y to the power 3 equal 1/10, and 1 to the power 1/15. This is the expected value of y to the power 4. Here we'll substitute in the formula. I think I have to use this page. We know that expected value, we are now computing expected value of c to the power 2. Fine. Expected value of c as shown here is 100 plus 400 expected value of y. Expected value of y, let's remember what is the value of the expected value of y. I think we find expected value of y by 1/3, and the expected value of y to the power 2 is 1/6. So here we'll substitute by the expected value of y with 1/3, and here we have 480 times 480 times expected value of y to the power 2, which is 1/6, plus 88 times 1/10 expected value of y to the power 3, plus 16 expected value of y to the power 4 was 1 to the power 15. Well, what we need is to just simplify all these numbers to find the final answer. Here we have the final answer already is computed here. I think just here we have 100, 400, 480, and 16. I think I have some error here. It was not 116, 160. I think I made a computational error at the end. But we have here expected value of y to the power 4 equal 1/15, and expected value of y to the power 3 equal 1 to the power 10 divided by 10. Then at the end, this expected value of c to the power 2. I don't have here the final answer, but at the end, just all what we need is to find all these value, and then subtract these, subtract from this value, or subtract from the expected value of c to the power 2 from this term, to have at the end the variance of c. I think we have many calculation here, but it's all they are all simple. It's not hard to do by yourself. Now move to the next or the final topic in this chapter, which is the moment generating function, and we have already studied the moment generating function. It's another expected value of a function of a random variable. This expected value take this form, and we call it m underscore y of t, expected value of exponential function to the power ty, and t move between negative h, and h is a positive constant. For a continuous random variable y with a BDF f of y, the moment generating function, and abbreviated by MGF, is defined by a kind of expectation. So expected value of e to the power ty. And if we treat this function as if it is g of y, then we'll substitute in the form of the expected value of a function of a random variable using the form of integration. So here is the function g of y, but in this concept we have this function equal to e to the power ty. It is said to be that if m of yt is exist, then all the moments are exist, and we call it exist if there is exist a constant h greater than 0, such that this function is finite within t between negative h and h. So outside this range, this function could be not defined. So it's okay, ما فيش أي مشكلة طبعا that this function to be defined undefined out of this range. At least we need some neighborhood around the t. takes the value from negative h to h, and this is enough to me to define a function to express the moment generating function. Another note, if this function exists for t lie within negative h and h for some constant h is positive, then all moments are exist. So if this function exists, then moment of any order exists. I mean the non-central moment. One can easily show that when we substitute for t by 0, this has to be 1, and we already proved this in the case of discrete random variable. Now move to the concept of the moment generating function as a tool to generate moment. In fact, this function is called the moment generating function because it generates the moment. In general, the earth moment about the origin can be found by evaluating the earth derivative of the moment generating function at t equals 0. And again, I'm repeating that we studied that before in the discrete case. We just are revising this information because these information are the same either for the discrete random variable or for the continuous random variable. So if we need to find the expected value of y, we need to find the first derivative of the moment generating function with respect to t, and then substitute in this derivative by t equals 0, then the result will be the expected value of y. If we find the second derivative with respect to t and then substitute in the formula of the second derivative by t equals 0, then we'll find or we obtain the expected value of y to the power 3. Again, if we try to differentiate for a third time and then substitute in the third derivative by t equals 0, this will be expected value of y to the power 3. And so on for any r. Again, there are some properties, and we discussed those properties before in the discrete case. If we have a variable or a function of the variable, say for example z equal y plus a. So if we know the moment generating function of y, can we detect the moment generating function of z? Yes, by this rule. If z equal y plus a, then the moment function, this is the moment function of z, will be e to the power at, this is the constant times t, then multiplied by the moment of the moment generating function of y. Okay, if z in another function is a constant time the variable, in this case the moment generating function of z will be the moment generating function of y, but after multiplying t by b, substituting for each t in the moment of y by bt. If we generalize this formula to z equal a plus y divided b, then this will be the moment of z given by e to the power ab, a divided by a divided b times t, multiplied by the moment of y at t equal t divided b. Now move to solving some exercises. Here we have an exponential function, and y is a negative random variable. This random variable, we need to find the moment generating function of y, and use it to find the first 3 moments, and then we need to find these formulas. Now move to find the moment at the first. Again, here we have the PDF takes the form e to the power y, and y is a negative random variable, and we need to find y of t, which is the expected value of e to the power ty. Again, this is g of y. Then this expectation is given by negative infinity to infinity for this function times the BDF dy, and then we'll substitute from these limits by the limits over which the BDF is defined, which is from negative infinity to 0, as shown here from the support. So this will be integration from negative infinity to 0 e to the power ty times e to the power y dy. Then we have 2 exponential functions, so we can multiply them by adding the power. So this will be negative infinity to 0 e to the power, and we have y as a common factor, y times t plus 1 dy. This is a exponential function. The integration of this exponential function is the same, e to the power y t plus y, but if there is a coefficient multiplied by y, we have to, we have to multiply, divide it by this coefficient t plus 1, all this, and then substitute from negative infinity to 0. When y time, when we substitute for y equals 0, this will give us e to the power 0. E to the power 0 divided t plus 1 minus t plus 1 e to the power the limit when y tends to negative infinity of this function. What is the value of this limit? We know that y is a negative value. So if y is a negative value, then this limit will tend to 0, because e to the power negative will be e to the power negative infinity will be 1 divided by e to the power infinity, and 1 divided infinity equal to 0. What keep this exponent? What keep this exponent tends to, again, we have y is a negative, right? So it's always takes negative value. So if y tends to negative infinity, if t plus 1 was a negative value, again, if t plus 1 is a negative value, then this negative multiplied by negative of the value of y, so e will be raised to the power infinity. So this limit will never tend to 0. So we have a condition here to this limit to be 0. So t plus 1 have to be positive, have to be greater than 1. So which means t have to be greater than negative 1. Okay, if this condition is satisfying, so this limit will be tends to 0. I hope this is understood for all of you. So at the end, the moment generating function of y will be t plus 1 raised to the power negative 1 and t greater than negative 1. Let's check the answer. Yes, 1 to the power 1 divided by t plus 1 and t greater than negative 1. What we need now is to use this moment generating function to find the first 3 moment. Again, we have here a moment of y equal to 1 1 plus t. So this is the moment generating function of the random variable y, and we need to find the first 3 moments. To find the first moment, this means we need to differentiate this moment generating function with respect to t. So we have a power function. This will be negative 1 times t plus 1 all to the power negative 1, which is negative 2. And we have t multiplied by 1, so there is no derivative. Its derivative equal to 1. This at the end, it's negative 1 times t plus 1 all to the power negative 2. So m prime of y at t equals 0 equal to the expected value of y. This will be negative 1 times 0 plus 1 all to the power negative 2, which is negative 1. So expected value of y equal to negative 1. Now, to find the expected value of y to the power 2, this means we need to differentiate the moment for the second time. So this means we will try to find the first derivative of this function, which is negative 2 times negative 1, which is 2, times t plus 1 all to the power negative 3. So expected value of y to the power 2 simply is the second derivative of the moment generating function, but after substituting for t equals 0. This will be 2 times 0 plus 1 all to the power negative 3, which is 2. So expected value of y to the power 2 equal to. Now, to find the expected value of y to the power 3, we need to find the third derivative of the moment generating function. We can write it like this. So this means we need to find the derivative of this function. So here, negative 3 will be multiplied by 2 to give us negative 6. T plus 1 all to the power negative 4. Then the moment generated function, the third derivative of this moment generated function at t equals 0, in fact, this will give us expected value of y to the power 3. This will be negative 6 times 1 to the power negative 4. So it is negative 6. Now we find the first and the second and the third moment. Fine. I think the next exercise was to find the variance of y. Variance of y equal to expected value of y all to the power 2 negative the expected value of y all to the power 2. Expected value of y to the power 2 equal to 2. Here, 2 minus expected value of y all to the power 2. Here we have expected value of y equal to negative 1. So we have negative 1 all to the power 2. This will be 2 minus 1, which is 1. This is the variance of y. The last question, so we already get the same result. The variance equal to 1. The expectation of y equal to negative 1. The expected value of y to the power 2 equal to 2. And the expected value y to the power 3 equal to negative 6. Now we need to find expected value of a function which is e to the power 3 y divided by 2. We need to find expected value e to the power 3y divided by 2. Again, expected value of e 3y divided 2. Here we imagine that we have another variable c equal to z, which is 3 divided 2y. And we know that the moment of z, in fact, this means this expected value, meaning that we need to find mz of t. So we need to find m of 3y divided 2 of t. And here we have 3 divided 2 is a constant multiplied by y. So this will give us the moment of y, applying the properties of the moment generic function. This will be the moment of y, but at t equal 3 divided 2 times t. So all what we need now in the moment generating function of y, which is 1 plus t all to the power 1, and the t greater than negative 1, is to substitute for each t by 3 divided 2. That's what we need now. So the moment of z will be 1 plus 3 divided 2 t all to the power negative 1. And don't forget to substitute for the new t also in the domain. So this will be 3 divided 2 t greater than negative 1. So this means t will be greater than negative 2 divided 3. So this will be the moment generating of the new variable z, and the z equal to 3 divided 2 y. Here we have the answer. We have the moment for the new variable equal to 3t divided 2 plus 1 all to the power negative 1, and t greater than negative 2 divided 3. And now we have the last exercise. Here we have a random variable y that have a moment generic function defined by this formula, and we need to find from this moment generic function of y two functions of a random variable y. X equal y divided by 3 and z equal to y plus 5. Here I write the question here. We have the moment generic function of y and need to use it to find the moment for each x and z. To find the moment of x, this means to find the moment of y divided 3 of t, and then here y is multiplied by 1/3. So this will be the moment of y, but for t multiplied by 1/3. So all what we need now is to substitute in the moment of y by each t equal 1/3. So this will give us 3 times t over 3 plus t over 3 plus 8 times t over 3 all to the power 2, which is e to the power t plus 8 to the power 9 times t to the power 2. This will be the moment of the variable x. Now move to find the moment of the variable z, which is the moment of 2y plus 5 of t. Remember, if we have a constant that is not multiplied by y, it show up here out of the moment of the formula of the moment, but it will be raised to 5, the same constant here, times t. So e to the power 5t. Let's try to write it again. E to the power 5t. This multiplied by the moment of y of t, but t multiplied by the constant that is multiplied by y here. So t will be multiplied by 2. Then this will be e to the power 5t times e to the power. Each t here above in the moment of y will be 2t. So 3 to the power multiplied by 2t plus 8 multiplied by 2t all to the power 2. So at the end, let's move this value above here. This will be e moment of z. The moment of z will be e to the power 5t times e to the power here 6t plus here 2 to the power 4 to the t to the power 2, which is 4, times 8, which is 32 t to the power 2. This is the moment of, we can multiply both exponential function by adding the power to have at the end e to the power 11t plus 32 t to the power 2. This is the moment of z. If we move to the answer there, yes, 11t plus 32 t to the power 2, and here we have the moment of x. At the end here we have one exercise, and I gave you the final answer, so I need you to practice and do check if you get the similar answer, and I receive any question by email, so can ask me at any time. At this point, in fact, we finish chapter 4. We cover all what we need to know about the continuous random variable and the properties of the probability density function, cumulative density function, how to compute the variance expectation and the moment generating function. We'll next discuss in the next chapter some families of the probability density function of a random variable that is exist and applicable in the real life. أستودعكم الله.